Good afternoon, my YouTube viewers. It is Crystal here, and I wanted to make another video for you. And this video that I'm making is going to be about the binomial distribution. So I'm going to be discussing the binomial distribution and the functions that go along with it. So the first thing that we're going to talk about is how to actually make a binomial distribution. So this first script is going to be actually how to make a binomial distribution. So it's written in Python, and I've used Google Colab as the program that I'm using to write it with. So the first thing we're going to do is import NumPy as NP to perform numerical computations, and then import matplotlib.pyplot as PLT to visualize the data. So we're going to set the parameters for the binomial distribution is number of trials is n, probability of success for each trial is 0.5, that's 50%, and the size is going to be 10,000. That's going to be the number of experiments. So we're going to generate the binomial distribution data, which is binomial data equals np.random.binomial n, comma, p, comma, size. And then that's your binomial data. And now what we're going to do is we're going to plot it with matplotlib. So plt.figure, fig size is 10, 6. That's going to be the size of the figure. plt.hist, that's a histogram, brackets binomial data, bins equals np.arrange, n plus 2 to the square root of n plus 2. H color is black and alpha is 0.7. The title is binomial distribution. The X label is number of successes. The Y label is frequency. The X ticks is range equals n plus 1. On the grid, the axis is Y, the line space is dash dash, the alpha is 0.7, and then we're going to show it. So this is the actual binomial distribution, and you can see that it is discrete from 0 to 10, with the mean being around 5. So now we're going to print some summary statistics. The mean equals np.mean, brackets binomial data, std.dev equals np.std, that's your standard deviation, binomial data. Then you print your mean and you print your standard deviation. And so the mean is 4.9994 and the standard deviation is 1.5. So I was pretty much close to the mean. I was close to the mean just by doing a visual inspection of it. And then the number of trials is 10. And so X is your number of successes is 0 to 10. So now what we're going to do is we're going to talk about the central limit theorem. And what the central limit theorem is, it doesn't matter what the distribution is, but if you have a really large population with the distribution, and in this case it's going to be a binomial distribution, and then you take samples of that distribution, then the means of all the samples that you take are going to be a normal distribution, normally distributed, especially if it's enough samples and if the samples are large enough. That is your central limit theorem. So we're going to go ahead and talk about the central limit theorem. So we're going to import NumPy as NP to perform your numerical computations. We're going to import matplotlib.pyplot as PLT to visualize the data. So now we're going to set the parameters for the binomial distribution. N equals 10, that's your number of trials. P that equals 0.5, that's the probability of success for each trial. And population size, I think it's going to be 100,000. So that's going to be your number of experiments. So now we're going to generate a binomial distribution from the data. So binomial data equals np.random.binom, brackets n, comma p, comma population size. And now we're going to set up the parameters for the binomial. Let's see, parameters for sampling. So sample size equals 30, num samples equals 1,000. So you're going to have 1,000 samples. So now we're going to calculate the sample means. So sample means equals empty list for underscore and range num samples. Samples equals np.random.choice binomial data, comma, sample size. Sample mean equals np sample, np mean sample, and sample means equals sample means dot append sample mean. So you're gonna append all of the sample means to the sample means list. So now what you're going to have is you're going to have a list of sample means. So we're going to plot the population distribution. So then we're going to plot a subplot of 1, 2, 1. We're going to plot a histogram of the binomial data. Bins equals np dot arrange n plus 2, and it's going to be the square root of that. And then edge color equals black, alpha equals 0.7. The title is original binomial distribution. The X label is number of successes. The Y label is frequency, and the X ticks is range n plus 1. Now we're going to plot the distribution of the sample means. So plt.subplot 1, 2, 2. And then we're going to plot another histogram, pld.hist, bracket sample means, comma, bins equals 30, edge color equals black, alpha equals 0.7, and then the title is distribution of sample means. X label is sample mean, Y label is frequency, and then you're going to have a grid of axis equals Y, line space equals double dashes, and alpha equals 0.7. And so now we're going to plot a tight layout and we're going to show it. So these are your two distributions. You've got the original binomial distribution, which we have previously made, and then we're going to have the distribution of the sample means, and you can see that the distribution of the sample means is very close to a normal distribution. So now we're going to print some optional statistics. Mean of sample means equals np.mean sample means. STD DEV of sample means equals np.std sample means. And then we're going to print out these statistics so you can see that your mean of sample means is 4.99 and standard deviation of sample means is 0.29. So that's it. So that proves your simple central limit theorem that when you have enough samples and you take the means of those samples, then the means of those samples are going to equal a normal distribution, and it does look very close to a normal distribution. Now we have a sample question with the binomial distribution. Basically, the IRS estimates that 5% of many high net worth tax returns are fraudulent. These tax returns will contain errors that are purposely made to cheat the government. Although these errors are well concealed, suppose that an IRS audit will uncover them. If 100 tax returns are audited, what is the probability that 5 fraudulent tax returns will be uncovered? And so we're going to use SciPy to calculate the probability. So parameters is the number of trials or audited returns is 100. The probability is 5%. That's the number of fraudulent returns. And then the K is the number of success is fraudulent returns. So probability equals stat stat by known PMF, and that is the probability mass function of K, number of successes, N, number of trials, and P, probability. And then so we print the probability. The probability is 18%. So we have another question based upon the IRS. if 250 returns are audited, what is the probability the IRS will uncover at least 15 fraudulent returns? And again, we're going to use scipy.stats for that. The parameters is 250 audited returns. The probability is 5%. That's fraudulent returns. And then your cumulative probability function equals stats.binomial.cdf, and 14 is the highest number you can go, because it's like 15 minus 1. And then n is the number of trials, and then p is your probability. So we calculate the probability at least 15 equals 1 minus cumulative probability. And then we print that off, and it's 27%. So you'll notice that if you want at least 15 fraudulent returns, then it's going to have to be 15 minus 1. And then that's also going to be like, they don't call it that, but I think it's going to be like the survival function, but they don't call it that in this particular exercise. Now we're going to do another practice question. If 250 returns are audited, what is the probability the IRS will uncover at least 15, but at most 20 fraudulent returns? Again, we're going to use SciPy for that. So n is 250, that's your number of trials. P equals 5%. Now we calculate the cumulative probability for 20 or fewer fraudulent returns. So cumulative probability 20 equals stats.binomial.cdf, that's cumulative distribution function, and 20, comma, n, comma, p. And then now we're going to calculate the cumulative probability for 14 or fewer fraudulent returns. So cumulative probability 14 equals stats.binomial.cdf, and it'll be 14, comma, n, comma, p. And now we calculate the probability for finding between 15 and 20 fraudulent returns. So probability 15 to 20 equals cumulative probability 20 minus cumulative probability 14. And then we print that up, and it's 25.63%. So we have another question. What is the probability that out of 250 returns, no fraudulent return is uncovered? Again, we're going to use SciPy for that. So we have 250 trials, that's your n. Probability is going to be 5%, and k is your number of successes equals 0. Calculate the probability. Probability of no fraudulent equals stats.binomial.pmf. PMF is your probability mass function, brackets k and p, and it's essentially going to be 0%, because it's going to be 2.69 to the negative 6th power. So it's going to be essentially 0. So now what we're going to do is we're going to make a probability mass function just with the binomial. We're going to make a probability mass function with the binomial. So binomial distribution. So we're going to import NumPy as NP. So that's going to calculate your numerical values. We're going to import matplotlib.pyplot as PLT. That's going to visualize the data, and we're going to import scipy.stats as stats, and that's going to give you your scientific computations. N equals 5 is your number of trials. P equals 50%, which is your probability of success. So possible number of successes is k equals np.arrange bracket 0 over n plus 1. PMF values equals stats.binomial.pmf. That's your probability mass function, k and p. And then we're going to plot it. So we're going to plot plt.stem, k, comma, PMF values, comma, base format, space. Then the X label is going to be your number of successes. Your Y label is going to be your probability, and your title is PMF of binomial distribution with end trials at 50%. Then your X tick is going to be K, and then we're going to show it. So this is our PMF of a binomial distribution with n equals 5 and probability equals 50%. So you can see that we've made that up. So we're going to have another probability mass function that this is not going to be a distribution in particular, but I went ahead and included it in the binomial distribution. It's going to be a discrete distribution, so it doesn't necessarily have to be a binomial. We'll just say right here. So it's just a discrete distribution. So we have our possible outcomes for a fair six-sided die is X is an array of 1 to 6, and then we're going to have the corresponding PMF values. So PMF values equals 1 over 6 times 6. And then what we're going to do is we're going to plot it. So we're going to plot the stem, brackets X, PMF values, and then base format is spaces. X label is outcome, Y label is probability, title is PMF of a fair six-sided die, X ticks is X, Y limits is 0, 0.2, and then we're going to show it. And so you can see for a fair six-sided die, each outcome is the same for all 6. So it doesn't matter which one they are, they're all 6. So we're going to have another practice question for the binomial distribution. Suppose you are conducting a survey and you find that 70% of people in a city prefer coffee over tea. You randomly select 10 people from the city and ask them about their preference. What is the probability that exactly 7 out of the 10 people prefer coffee over tea? And then so we're going to use SciPy to make this calculation. Parameters for the binomial distribution are n equals 10, that's number of trials. Probability of success is 70% because 70% of people prefer coffee over tea, and the number of successes is 7. That's going to be 7 out of 10 people prefer coffee over tea. We're going to calculate the probability using PMF. So probability equals stats.binom PMF KNP, and then we're going to print the probability. The probability is going to be 26.68%. We're going to do a cumulative distribution function of and this is going to be not the binomial, but it will be a discrete distribution. Okay, and so the possible outcome, we're going to be using Matplotlib to plot it. Possible outcome is X equals an array or a list from 1 to 6. Corresponding CDF values equals 1 to 6, 2, 1 over 6, 2 over 6, 3 over 6, 4 over 6, 5 over 6, and then 1. Because you've got to remember that the cumulative distribution function, it has to add up to 1. And then so we're going to plot this out. So plt.step X CDF values where post label equals CDF. Then the X label is outcome, Y label is probability, title is CDF of a fair six-sided die, X ticks is X, Y lim is 0, 1.2, so that's your limit. Legend is, there is no legend, there's a grid is true, and they're going to show it. So these are your steps. This is the visualization that you get, and it's going to be for a discrete distribution. So we're going to do another little exercise, and this is the cumulative distribution function for a binomial distribution. So we're going to import numpy as np to perform numerical computations. We're going to import matplotlib.pyplot as plt to visualize the data, and we're going to import scipy.stats as stats to perform scientific computations. So we set the parameters for the binomial distribution. N equals 10, that's your number of trials. P equals 50%, that's your probability of success. And then we define the range of K values, that's your number of successes. K equals np.arrange brackets 0, n plus 1. And then we calculate our CDF values. CDF values equals stats.binom.cdf brackets K, n, p, and then we plot this out using matplotlib. So plt.step, it's going to be K, CDF values, where post label equals CDF. X label is number of successes. Y label is cumulative probability. The title is CDF of a binomial distribution. N equals 10, P equals 0.5. X ticks is K. Y lim is 0, 1.2. There's no legend. It's going to be a grid, and we're going to show it. And you can see that this is your CDF of a binomial distribution of N equals 10 and probability equals 0.5. And as you can see that with the CDF, that's cumulative distribution function, as it must equal once. So now we have another practice question for you. A quality control inspector at a factory tests 15 light bulbs from each batch to determine if they meet quality standards. Historically, the probability that a light bulb meets quality standards is 0.8. The inspector wants to calculate the probability that at least 12 out of the 15 tested light bulbs meet the quality standards. So we're going to import scipy.stats as stats to perform our scientific calculations. So we're going to set the parameters for the binomial distribution as n equals 15, that's your number of trials. P equals 0.8, that's your probability of success. And K equals 12, that's your number of successes. So we're going to calculate the cumulative probability using the CDF. So cumulative probability equals stats.binom.cdf brackets K and P, and then your cumulative probability is 60.2%, which we print out. And now we're going to look at the survival function. And so what the survival function is it's that if you pick a number, and it has to be over that number, whereas on the probability mass function, it has to be under that number. With the survival function, it has to be over that number. So we're just going to do, we're going to calculate the survival function now. We're going to use matplotlib.pyplot as PLT to visualize it. And so this can be for any discrete distribution. So the probable outcomes for a fair six-sided die is a list of 1 to 6. Corresponding survival function values is a list of 5 over 6, 4 over 6, 3 over 6, 2 over 6, 1 over 6, 0. And now we're going to plot it. So plt.step x, survival values, where is post, and label is survival function. The x label is outcome. The y label is survival probability. The title is survival function of a fair six-sided die. X tick is x. Y limit is 0, 1.2. And then there's no legend, and it's on a grid, and we're going to show it. So here is your survival function for a six-sided die. So you'll notice that as it approaches 6, it gets closer and closer to 0. So now we're going to do the survival function for a binomial distribution. We're going to import NumPy as NP, which is your numerical computations. We're going to import matplotlib.pyplot as PLT, which visualizes the data. We're going to import scipy.stats as stats. So we're going to set the parameters for the binomial distribution is n equals 10, that's your number of trials. P equals 0.5, that's your number of successes. And then we're going to define the range of k values, number of successes. K equals np dot arrange, bracket 0, comma n plus 1. We're going to calculate the CDF values. Is CDF values equals stats.binom.cdf, and that's cumulative distribution function, KNP. We're going to calculate the survival function values. Survival function equals 1 minus CDF values. And then we're going to plot it on using matplotlib. So plt.step K survival values where post label equals survival function, plt.xlabel equals number of successes, y label equals survival probability, title equals survival function of a binomial distribution, whereas n equals 10, p equals 0.5, x ticks is k, y lim is 0, 1.2. There's no legend and it's on a grid. And then when we plot it, you can see that it is the plot. And so as the number of successes approach 10, the survival probability approaches 0. So that's it for your survival function. So now what we're going to do is we're going to do a practice question on the survival function. A software company releases an update to their product, and they estimate that 80% of users will successfully install the update without any issues. Suppose the company randomly selects 20 users to monitor the update process. They want to calculate the probability that more than 16 out of 20 users successfully install the update. And then so we're going to use SciPy to perform our numerical computations. So we're going to set the parameters for the binomial distribution. N equals 20, that's your number of trials. P equals 80%, that's your number of successes. K equals 16, that's your number of successes. So we calculate the cumulative probability, which is stats.binom.cdf, KNP. We're going to calculate the probability. Survival probability equals 1 minus cumulative probability, which is 41.14%. So now we've got the hazard function. And then so what the hazard function is, what's going to happen if it goes over a certain point. And then so import NumPy as NP, which performs numeric computations. And we're going to import matplotlib.pyplot as PLT, which is going to visualize the data, days, and corresponding PMF values. That's your probability mass function. Days equals np.array 1, 2, 3, 4. PMF values equals np.array 0.1, 0.3, 0.4, 0.2. We're going to calculate the CDF values. CDF values equals np.comsum PMF values. Calculate the survival function values. Survival values equals 1 minus np concatenate 0, CDF values, brackets, colon, -1. And then we're going to calculate the hazard function values. So hazard values equals PMF values over survival values. And then we're going to plot that. So we're going to PLT using matplotlib. So plt.step is days, hazard values, where, mid, label, hazard function. X label is days, Y label is hazard rate. Title is hazard function of discrete distribution. X tick is days, Y lim is 0, 1.2, and the grid equals true. So the hazard function of so this is what we've plotted, and so this is a hazard function of discrete distribution. So as you can see, as the days increase, the hazard function increases. So now we're going to do another hazard function with a binomial distribution. Just let me calculate this. So the next one is going to be a hazard function with the binomial distribution. So we're going to import numpy as np to form our numeric computations. We're going to import matplotlib.pyplot as plt to visualize the data, and scipy.stats as stats to perform our scientific computations. So we're going to set the parameters for the binomial distribution. N equals 10, which is your number of trials. P equals 0.5 is your probability of success. And we're going to define the range of k values, which is your number of successes. K equals np dot a range 0, n plus 1. And we're going to calculate the PMF values. PMF values equals stats dot binom dot PMF KNP. We're going to calculate the CDF values. CDF values equals stats.binom.cdf KNP. Now we're going to calculate the survival function values, and the survival function is the complementary of the CDF. So survival values equals 1 minus CDF values. We're going to calculate the hazard function, and it says avoid division by 0 for k values where survival function is 0. Hazard values equals np dot where brackets survival values greater than 0, comma PMF values over survival values, comma np dot inf. Now we're going to plot this using matplotlib. We're going to plt.step k, comma hazard values where mid label equals hazard function. plt.xlabel is number of successes is k. Y label is hazard rate. Title is hazard function of binomial distribution. N equals 10 and P equals 0.5. X ticks equals K. Y lim equals 0, 1.2. There is no legend, and it has a grid, and you can see the hazard function of a binomial distribution for n equals 10, p equals 0.5. So you can see that as the number of successes increases, the hazard rate increases as well. So we've got another little practice questions for you. A company manufactures electrical components and tests them for reliability. The probability that a component passes the reliability test is 90%. The company tests 15 components in a batch. You want to calculate and interpret the hazard function to understand the probability of a component failing at a specific test number, given that it passed all previous tests. So in order to do this, we're going to import numpy as np, which performs our numeric computations. We're going to import matplotlib.pyplot as plt, which visualizes our data, and we're going to import scipy.stats as stats to perform our scientific computations. So the parameters for the binomial distribution, n equals 15, that's your number of trials. Probability is 0.9, that's your probability of success. We're going to define the range of k values, that's your number of successes. K equals np dot a range 0, np plus 1. We're going to calculate the PMF values. PMF values equal stats.binom.pmf. It's going to be K and P. We're going to calculate the CDF values. CDF values equal stats.binom.cdf brackets K and P. We're going to calculate the survival function values, which is a complementary CDF. So survival values equals 1 minus CDF values. We're going to calculate the hazard function values, and we're going to avoid dividing by 0. Hazard values equals np.where, survival values greater than 0, PMF values over survival rates, comma, np.inf. And we're going to plot this using matplotlib. So plt.step brackets k, comma, hazard values, where, mid, label, hazard function. X label is number of components passing k. Y label is hazard rate. Title is hazard function of a binomial distribution. N equals 15, P equals 0.9. X ticks is K. Y lim is 0, 1.2. There is no legend, and it's on a grid. So we plot it, and this is what we have. And you notice that as you have the number of components passing K increases, it gets closer to 1. And that's it. That's everything that I have for the binomial distribution. And I know that this video has taken a long time for me to go over because I had a lot of information to go over, but I wanted to make sure that I got everything: the probability mass function, the cumulative distribution function, the survival function, and the hazard function before I made this video. So if you like my video, please like and subscribe. I would like to thank you very much for watching the video because I know it was long, but it did cover a lot of really important information. And thank you so much for watching my video. I look forward to making another technical video for you very soon in the near future.